Great. So topic 6 was all about factors that affect rates of reaction and seeing how we could monitor some of that in the lab. We're going to go a little bit deeper now and expand that into this idea of a rate expression, and then why this is important, because it tells us about the mechanism of a reaction, how things are actually colliding and reacting, what pathway they're following. So the whole purpose, really, or one of the large purposes of investigations into rates, is to get this idea of mechanisms. How do things collide? How do they react? So that's what we're covering. And we're going to start with this idea of orders of reaction. So how does changing the concentration of a reactant affect the rate? Because it turns out, depending on the mechanism, changing these concentrations has a different impact on the rate of reaction. And so we've seen that we can work out these rates in topic 6. And there are 3 orders of reaction that we need to be familiar with: 0th, 1st, and 2nd. Now, if we describe a reactant as being 0th order, its concentration doesn't affect the rate of reaction. Might seem a bit odd, but it doesn't matter how much of it there is, it doesn't have any effect on the rate. If something is described as 1st order, then it's directly proportional. In other words, doubling its concentration would double the rate. If something's 2nd order, then it has a squaring effect. So maybe we can look at this graphically. So something 0th order, as we said, its concentration doesn't affect the rate. So there we go. Whatever its concentration is, it's not affecting the rate of reaction. And as we can see here, over time, no matter how much of it is, it just gets steadily used up. It doesn't matter whether you've got lots of it, a little bit of it, it's just steadily used up. So that's a 0th order reactant. Here, something's 1st order, then we've got this directly proportional relationship. So you double the concentration, you double the rate. And if we were to plot concentration against time for that, we'd notice this kind of decay curve, which might be familiar to some physicists for radioactive decay. And we can describe this as having a constant half-life. In other words, the time taken for the concentration to fall to half its original value is always the same. So if you measure off a pair of concentrations and you look at the time taken for those changes to take place, you would find that it was constant. So we've got this constant half-life. Plot looks something like that. 2nd order, where we've got this squaring effect, we can see a different shaped curve. That's a bit tighter there, coming down. It's much steeper than that one. And if you were to plot rate against concentration squared, then you would get that proportional line there. Right, so this idea of 0th, 1st, and 2nd order can be written down, linked to the rate, using our rate equation. And in that rate equation, we have this constant of proportionality, which is called the rate constant. And the units of that rate constant are going to depend on what the equation looks like. Right, rate constants are also affected by temperature. We'll maybe see what K is all about when we look at some of these examples. So here's some experimental data. And you can work through this yourself, but if you just, maybe we'll just look at experiments 1 and 2. So we're choosing experiments where only one of the things has changed. And you can see here A stayed the same, C stayed the same. Well, B has doubled. What's happened to the rate? That's also doubled. Therefore, from those definitions, B must be 1st order, which means in my rate equation, it's going to be raised to the power 1. Right? Anything that's 0th order isn't going to appear, because anything to the power 0 is just equal to 1, so we can leave that out of the rate equation. But here's my rate equation. Rate is proportional to A, so A must be 2nd order, looking at that squaring power there. B's 1st order. If I put in my rate constant, I'm allowed to say it's equal to that. And I can actually take one of these experiments, put the values in, and I can work out a value for the rate constant. And as I said, if I consider the units, rate is measured in this, concentrations measured in that, I can solve it and get the correct units for K as well. It's a question for you to practice. So you pause me, have a go at that. There's the answer. Now, leading on to mechanisms. So couple of words to define here. Molecularity, how many reactant particles are taking part in a particular step. So unimolecular means there's one thing involved. Bimolecular probably means you've got two things colliding. The rate determining step, very important definition this, worthy of a bit of highlighting I think. So this is our slowest step in a reaction, okay? And it's the one that kind of determines how quickly the whole process occurs. So if you've got 2 or 3 steps happening, one of them is going to be slower than all the others. That's the one that holds everything up, and that's kind of our most important one, if you like. So the stuff that's in our rate equation, the stuff that we're seeing here, these are involved with our rate determining step, right? Rate determining step is the slowest step. It's the one with the highest activation energy. It's the one that is slowing or determining how quickly our reaction occurs. So things that appear in the rate equation appear in the rate determining step. That's probably an important thing to remember when you're trying to define a mechanism. Right, catalysts, to do what they do, they play a part in changing the energy. I guess we saw they reduced the activation energy, so they're involved with this rate determining step. And there we go, definition of a catalyst: speeding up a reaction using an alternative mechanism, lower activation energy. Right, so this is what a mechanism looks like, iodination of propanone. And you can see here that the experiments have shown that this is my rate equation. There it is. And this is the actual mechanism. And you can read through this, but the one thing I wanted to highlight was that if we take our rate determining step, this is our rate determining step, this is the thing, this is a reactant in our rate determining step, we would expect that to be in our rate equation. So if we just looked at this mechanism, I would be expecting that rate equals K CH3COH plus CH3. However, this isn't actually a reactant. This isn't something that I'm adding in my solution. So I can't have that in my rate equation. I've got to think, well, where did this come from? And this has come from here. So instead of saying that, I'm actually going to say, well, CH3COCH3 H plus, this essentially, right? So whilst this is in our rate determining step, this is what we'd expect to see in the rate equation. Because it's not one of my actual starting materials, I'm going to ask myself, well, where did it come from? And it's actually made from one of these and one of these. So that's why that rate equation looks like that. You can see that again explained just there. One last thing to consider when you're proposing mechanisms is you're very often going to have to come up with some sort of intermediate. So transition state's very short-lived, high energy. There might be something that sticks around for a little bit longer, right? And so in this example here, it would be XY as my intermediate, and then that then goes on to form products. Okay, so you can see these intermediates and transition states on these energy level diagrams. Great.